So, in the chapter motion, we will see that the graphical representation of motion, in which way we can represent the motion uh, in the form of a graph. So, let us suppose there is an object here exactly here and this object is moving along this direction, and let us suppose we have a mechanism by which we can take its photograph after each second, after 1 second, and only we can take its photograph after 1 second. We have set the shutter, we have set the camera like that. So, if it is somewhere here, uh, wherever it is, after 1 second photo will be clicked. So, let us suppose after 1 second object reached here, so its photo will be clicked. After 1 more second it reached here, again if its picture is clicked, after 1 second, after 1 second, after 1 second, and so on. After each second, if its picture has been taken, this is not the graphical representation, by the way. It is just an I want to build a concept over it. So, here it is. Now, I will give you another scenario. This time, let us suppose the object is same. First, we have taken its photo here. Then, its next picture after 1 second was showing it there. After 1 second, it's showing it there. After 1 second, it's showing it there, and after 1 second it is showing it there, or even there. So, you can see, you can compare both of them, that in first picture at each second it is covering equal distance, and here at each second its travel distance is getting increased, and I am considering 1 second so that I can easily correlate with its velocity. Its velocity here is constant, distance upon time, distance upon time, time is 1 second. So, its velocity is same, whereas its velocity is increasing. Another case I want to take here, from where I have to start, but I am ending it here. There is a object and again we are taking its pictures. So, after each second, first second it was there, clicked again it was there, clicked again it was there. So, let us suppose over a period of time uh, I want to make it similar for each. I am removing these. Why? Because I have clicked the picture for 5 seconds. I have clicked its picture for 5 seconds. First second, click, 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 click. It's still there. I am clicking it for second case. I have got 5 different pictures. Here also, you can see a difference between all of these. And now I am going to plot these 3 motions in a displacement time graph. It can be distance time graph also, but I am drawing displacement time graph here. Okay. Displacement represented by S. Now these are new symbol. Displacement S, distance S, speed and velocity V. Just keep these things in your mind. And time along x-axis. Time along x-axis, displacement along y-axis. So I will call it A, it B, and it C. So for first case, the displacement, let us suppose the separation between me and A was this much. Let us suppose 2 meter it was, or no, it doesn't looking nice, here somewhere. So earlier it was, this is me, let us suppose I am at the origin, I am observing it, this object A, it is here at some separation. It is not the distance traveled, but its initial separation from the reference point, that is me. Then after 1 second, let us suppose here this is 1 second, this is 2 second, 3, 4, 5. This is our choice. I can take this as 1 second also. I can take half of it as 1 second. This is our choice, what we are considering as 1 second. So 1, 2, 3, 4, 5 up to so on. And its distances, let us suppose these distances are 2.5 meter. So that will be 5 and so on and so forth. So for first case, if I am drawing it, so at 0 time it was there initially. Let us suppose I was here, I was clicking its picture, it was here, so it was at a distance 2.5, somewhere here, because I have chosen such parameters, so I have to follow that somewhere here. So after 1 second it is still, see, don't get confused that it has traveled this distance. No, don't bother about this picture, this is separate from this graph. So after 1 second it didn't move, it is still at that much separation still. So its graph will go like this. Time is increasing, but its position is not changing. Its position is constant. Its distance or its displacement with respect to me is not changing. Case 2. After each click, it is traveling this distance. So earlier it was, let us suppose, here, then after 1 second it is here, after 1 second I have to change the ink, change the color, yeah, now it is good. After 1 second, after 2 second it is here, after 3 second it's here. So its graph is looking like a straight line. Straight line, of course, slant straight line. Okay, case 3. It was at 1 second, it was at 2.5. Oh, I think I have drawn it wrong. At 0 it was here. Yeah, of course all of the points are beginning from here. So after 1, yeah, okay, it was correct, it was correct. All right, so here earlier it was here, then after 1 second it has traveled half of the distance. I will change the color again. This one will be fine, I guess. It is here. After 2 seconds it has traveled a longer distance, somewhere here. After 3 it is out of scale, I guess, somewhere here. So its graph goes like this. It's not slant. Let me summarize all of these in a blank page. Oh, I have to change it. See, ST graph. Position time graph it is called, sometimes distance time graph, sometimes displacement time graph. I like the term position time graph. In some cases distance time graph and velocity displacement time graph are alike, but there is a difference, but I will reveal it later on. But first, there are some cases. First case, object at rest, or we can say stationary position. Its graph TS, its graph, if it is at the origin, it's coinciding, there's a straight line along the time axis. Or if it has initially some position, it will be again straight line parallel to the time axis. Remember that for rest position. For displacement time, remember that. Because see, don't just memorize, just think. If object is not changing its position, means it is at rest. Then uniform motion. Uniform motion. So here, okay, graph can start from here as well as I will draw with different colors. If it is starting from origin, it will be a slant line, slant straight line, uniform motion. Velocity is constant. And If already it is not at the origin, it is at it has some separation from the origin, then here it is. So in uniform motion, what happens, object, you can see this is the time. If I divide this motion into equal time intervals, I guess I have divided them into equal time, yeah, then the associated distance traveled will also be equal, this much, and for this time duration it is this much, and for this time duration it is this much. So in equal time interval, these are the equal time intervals, the distance traveled or displacement covered is same, constant. So such type of motion is uniform motion. Here velocity is same, we know, and we can say that at equal time interval distance traveled is equal, of course. Next, non-uniform motion with constant acceleration. As I told you, an accelerating car or freely falling object. Then just imagine if there is an object which is falling freely, then initially it was here, then its distance will keep on increasing in this way. You can try it at your home, drop something, take several pictures with high shutter speed, and you will see that it has traveled. First it has traveled very small distance, then a longer distance. So because of acceleration, and the graph will look like this. What is happening here? Distance traveled in equal time interval is increasing suddenly. First it was going slow, then it is going very rapidly. So this is when there is accelerated motion. Just remember these. Now as we have ST graph, so also we have VT graph, velocity time graph. And if I want to draw a velocity time graph for object at rest, I can draw nothing because velocity is 0 if object is at rest. People might say that this graph should also be empty. Yes, of course, but what I told, that if object is at a particular separation from the observer, then it will remain constant. So either this or this. But here either this still velocity is 0 or this still velocity is 0. So that will be a complete empty graph. VT graph will be empty for object at rest. Now for uniform motion, yeah, for uniform motion, as we know velocity is constant, then it will be a straight line parallel to time axis. Now what is it all about? People can relate from this to this, but no, there is no relation between them. It is associated with this. Here velocity is constant. So if I am drawing velocity, if velocity is same, if it is 5 meter per second, So it is still at each interval of time it is 5 meter per second. So it is showing uniform motion. Next, non-uniform motion with acceleration constant. It means there is an acceleration. It means velocity is increasing, maybe decreasing also, because acceleration is associated with change in velocity. Okay, here it is. So if it is starting from origin, if not, still if it has already some velocity initially, then graph will go like this. Slant, if acceleration is constant, slant with constant slope. These are possible graph. As I told you, distance time graph and displacement time graph can be all alike. Only the difference is distance can never be negative, distance can never be decreasing. See, if a graph goes like this can never be a distance time graph, because distance can never be decreasing. Distance can always increase. If a graph is like this is also not possible. Distance can never be negative. So also with speed. Speed, sorry, not here, here. Speed can decrease, but speed can not be negative. So remember, distance, if v is speed, it can never be negative. If for if s is distance, it can never decrease and never be zero, never be negative. Remember these things. Okay. What are we going to find from these graphs? Yes, of course, if there is an ST graph, then of course at a particular time interval we can find distance or displacement. And if it is a VT graph, then we can easily find at a particular time we can find its velocity. What else can we find? We can find its slope. If this is a graph line, then its slope of ST graph gives velocity, and slope of VT graph, I'm not saying that I am copying it here. This is a different kind of motion and this is different kind of motion. You know which kind of motion is this and you know which kind of motion is this. I'm just explaining slope in both the cases. Slope of VT graph gives acceleration. Though I haven't explained you about acceleration till now, but just keep it in your mind. that slope of ST graph give you velocity and slope of VT graph gives you acceleration. What is slope? So if there is a right angle triangle, then this side generally called perpendicular and this side generally called base. So perpendicular upon base is called slope. I would say altitude divided by adjacent, but see, it is easy, perpendicular upon base. So slope is perpendicular upon base, and most of the time student just memorize these things and say if there is a slope, slope means they say it's velocity, sometimes they say it is acceleration. No, slope is just slope, it is geometrical thing. Slope, you have often seen those slides in the park. So for children, its slope is less. For elder children, for younger children, its slope is less. For elder children, its slope is more. If there is a road, you have to, you want to run up to a hill. If it has higher slope, you will not try to run on it, but if it has a lesser slope, you can, you wish to run on it. So this is slope, and how are we going to find slope? Perpendicular upon base. If slope is more, you can see just by observation, or you can even calculate it. So this is how we find slope. So slope is just the geometrical concept. But if we are finding slope in ST graph, then it becomes velocity. In VT graph, it becomes acceleration. Coming back to, oh God, previous topic. Now apply the same concept here. Slope. Slope of this is just a straight line, it is not a slant line. So just a straight line, and it has no slope, it has zero slope, its slope is 0. And for ST graph, slope is velocity. Obviously its velocity is 0, it is at rest, its velocity is 0. So ST graph, slope of ST graph gives velocity. Slope is 0, velocity is 0. Here slope is constant. Here slope is same, here slope is same. For entire of it, slope is same. Because slope is same, slope is constant, so velocity is constant, velocity is same. And here for accelerated motion, velocity is increasing. And you can see slope of this graph is increasing. I should magnify this so that you can understand it in a better way. All right. If I divide this graph into a number of parts, for here there is, you can see I have taken interval, almost equal intervals, so that base is same, and then can see slope is increasing, and slope is increasing means slope of ST graph is increasing means velocity is increasing. Slope is increasing. Slope of ST graph, I am not writing it in all in full, but you need to write in full so that you not get confused. Slope of ST graph is increasing, it means its velocity is increasing, because slope of ST graph is velocity. Now slope of VT graph is